Hello, thanks for stopping by. My name is Ali Gambari, and I'm an assistant professor at Auburn University. I'm presenting our work using Fourier analysis and mutant clustering to accelerate DNN mutation testing. This work is done with the collaboration with Sasan Tewakkol from Google Research. As we know, DNNs are ubiquitous. They are used in many domains, including safety and mission-critical systems such as autonomous driving. And this creates a need for the robustness and accuracy of such system, which fuels the research on the quality assurance of such of DNN systems. Among several methods for quality assurance of DNNs, testing is widely adopted, but good performance on test data does not imply the robustness or generality of the DNN models. Mutation analysis is a promising method for quality assurance of DNN through assessing the quality of test dataset. Despite its potentials, mutation analysis is costly. In this paper, we propose DM-Sharp, which is intended to mitigate the costs associated with the mutation testing. The fundamental idea behind DM-Sharp is the notion of fast Fourier transform, which represents arbitrary functions, including mutant outputs, in terms of frequencies and amplitudes, which allows accurate approximation of those functions using only a few data points. DM-Sharp uses mutant clustering to group the mutants into behaviorally similar clusters and test a representative from each cluster instead of testing all the generated mutants one by one. DM-Sharp uses a third-party mutant generation engine, such as Deep Mutation. It then samples a small fraction of the test data points, for example, 1% or 5% of the test data points, and conducts discrete Fourier transform using fast Fourier transform algorithm, FFT, to generate FFT spectra of the mutants. The distance of the FFT spectra are treated as a proxy for the behavioral similarity/difference of the mutants. And then a clustering algorithm, parhack in this case, is used to cluster the mutants into behaviorally similar groups of mutants. Then a representative from each cluster is selected and tested using all the available test data points. The results can be used for approximating mutation score, which is what we have done in this work, or it can be used for other purposes such as mutation-based fault localization. We have used various DNN models of various types, such as image and text classifiers, and of varying sizes, ranging from tens of thousands of parameters to millions of parameters, to evaluate DM-Sharp and compare it to the related work. Our evaluation shows that in our dataset, DM-Sharp reduces the number of tested mutants by 35.71% on average, which translates to approximately 28.38% average reduction in mutation testing time at the cost of only 0.72% error in mutation score. We also compared DM-Sharp to several baseline techniques, including random mutant selection, which selects a random subset of the generated mutants for testing, random sample selection, which selects a subset of test data points but tests all the generated mutants, and boundary sample selection, which selects the test data points that are at the decision boundary of the original model. This method also tests all the generated mutants. We observed that in our dataset, random sample selection results in highest speedup, more than 63% on average, as it significantly reduces the size of the test dataset, which is also why we get highest loss, which is more than 82% on average. Boundary sample selection sits in the second place. It reduces the total mutation testing time by more than 67% on average. But this gain is at the cost of approximately 11% loss in mutation score on average. Surprisingly, random mutant selection resulted in a smaller loss of approximately 9% on average, while achieving more than 36% speedup. We also observed that DM-Sharp consistently outperforms other techniques in terms of average loss, which is less than 1%, and its average speed up, which is comparable to that of RMS. We have included much more details in our paper and have studied the technique from multiple perspectives. So I highly encourage to read the paper. We also have BM Sharp publicly available on Zenodo. Thanks for stopping by.